Entropy, a concept as enigmatic as it is fundamental, lies at the heart of our quest to unravel the mysteries of the universe. From the tiniest particles to the vast expanses of space, entropy weaves a complex tapestry that tells the story of creation, evolution, and the ultimate fate of all that exists. But what exactly is entropy? In simple terms, entropy is a measure of the amount of disorder or randomness in a system. The more disordered a system is, the higher its entropy. Imagine a tidy room with everything in its place. This room has low entropy. Now, picture the same room after a whirlwind of activity, with clothes strewn about and objects scattered haphazardly. This room now has high entropy. To help understand entropy, let's consider an example that a fifth grader might encounter. Suppose you have a bag of mixed candies. Some are red, some are blue, and some are green. If you reach into the bag without looking, the odds of grabbing a specific color are pretty much the same. This is because the candies are mixed up and disordered, which means the bag has high entropy. Now, if you were to sort the candies by color, putting all the reds in one pile, blues in another, and greens in a third, the bag would have low entropy because it is more organized. The story of entropy begins in the 19th century, as scientists like Sadi Carnot, Rudolf Clausius, and William Thomson, Lord Kelvin, grappled with the intricacies of heat, work, and energy transformation. Their groundbreaking work laid the foundation for the laws of thermodynamics, with the second law introducing the concept of entropy as a measure of the unavailability of a system's energy for useful work. But it was Ludwig Boltzmann who revolutionized our understanding of entropy, revealing its profound connection to the microscopic world of atoms and molecules. Through his pioneering work in statistical mechanics, Boltzmann showed that entropy is linked to the number of microstates, the countless possible arrangements of particles, that correspond to a given macroscopic state. This probabilistic interpretation of entropy shed light on one of the most perplexing aspects of our universe: the arrow of time. The unidirectional flow from past to future, the inexorable march towards disorder, all emerge as a consequence of the second law of thermodynamics and the statistical nature of entropy. Yet, amidst the relentless tide of increasing entropy, pockets of order and complexity arise, like islands of structure in a sea of chaos. From the intricate dance of molecules that gives rise to life to the cosmic web of galaxies that spans the universe, entropy plays a paradoxical role in both the emergence and the dissolution of the patterns that define our world. In the realm of information theory, entropy takes on new meaning, quantifying the degree of uncertainty or randomness in a system. The work of Claude Shannon and others revealed the deep connections between entropy, information, and the limits of communication, laying the groundwork for the digital revolution that has transformed our society. At the frontiers of physics, entropy and information intertwine in the most extreme environments known to science. The groundbreaking insights of physicists have shown that entropy plays a crucial role in our understanding of the universe, hinting at a profound link between the laws of thermodynamics and the nature of reality itself. From the birth of the universe to the ultimate fate of the cosmos, entropy shapes the grand narrative of existence. In the early universe, when matter and energy were compressed into an infinitesimally small space, entropy was at its minimum. As the universe expanded and cooled, matter began to coalesce, forming the first stars and galaxies. This process of structure formation, driven by the interplay of gravity and the fundamental forces of nature, represents a local decrease in entropy, as pockets of order emerge from the primordial chaos. However, the second law of thermodynamics dictates that the total entropy of the universe must always increase. As stars burn through their nuclear fuel, they radiate energy into space, increasing the entropy of the universe. Massive stars, in their death throes, explode as supernovae, scattering the heavy elements forged in their cores across the cosmos. This cosmic recycling process, while increasing entropy, also provides the raw materials for the formation of planets, and ultimately, the emergence of life itself. On Earth, the story of life is intimately connected to the story of entropy. Living organisms, from the simplest bacteria to the most complex animals, represent islands of order in a sea of chaos. Through the process of natural selection, life has evolved to harness the flow of energy, using it to maintain its complex structures and functions. Yet, even as life thrives, it too must obey the second law of thermodynamics. Every living thing, in the process of maintaining its own order, increases the entropy of its surroundings. In our struggle to comprehend the universe and our place within it, we find purpose, beauty, and the strength to confront the great unknown. The story of entropy is, ultimately, the story of the universe itself, a grand cosmic narrative of transformation, evolution, and the eternal cycle of creation and change. Through our relentless pursuit of knowledge, we may finally come to understand our place in the grand tapestry of existence, and to appreciate the fleeting beauty of our brief sojourn in the face of eternity.